Hey, everybody. Welcome back to Adventures in Machine Learning. I'm one of your co-hosts, Ben Wilson.
And Michael Burke. Hi, everyone.
Last couple episodes, we were talking about EDA, exploratory data analysis, and all the sorts of operations that we do in the data science profession when getting ready to build a model. Here's all the things that we really make sure that we need to do in order to make a healthy and potentially explainable model and something that we can maintain over time once it's shipped to production. And this week we wanted to talk about what's that next phase. Like we have, solid understanding of our features. We move to model training phase. And then what? What do we do when we need to understand how the training actually happened and what that model is potentially going to do once it's released into the wild?
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv. And I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Yeah, so last episode we talked about EDA, and this is hopefully going to be a reasonable segue. We're sort of skipping the hyperparameter tuning phase, but you can do that. You can just try a bunch of things. And a very important next step, especially in industry, is explaining what's going on. People tend to not trust black boxes, whether it be your boss, your boss's boss, or the consumer that you're selling to. So if you can explain exactly how feature X impacts Y, that's really, really valuable. And that can even inform the model that you choose, how you tune it, and a variety of other things. So we were thinking we would start simple with linear regression, which is actually super not simple, and then get into decision trees, and then maybe talk about Shapley and deep learning and some other more high-level topics. Sound good to you, Ben?
Mm-hmm.
Cool. So starting off with linear regression, most people know that it fits X against Y and finds linear relationships. And ignoring GLMs where it transforms the data so that it can fit a nonlinear relationship, we're just going to talk about linear regression with OLS, so ordinary least squares, super fast. It's my favorite out of the box. I guess it is an algorithm, but it's my favorite out of the box tool, super interpretable. So Ben, how would you go? Let's say you've done EDA, you've done all your feature engineering, and you have a great data set. You go in, put in a linear regression model with 5 features and 1 Y variable. What would be your first step in understanding what that model is actually doing?
So after I train, like you said earlier, we have a whole bunch of hyperparameter tuning stages, and what that's doing is automating this process that you just asked about. Like, hey, the model is trained on some data. We need to perform a validation step. And that means we typically take the data set and split it into 2 or 3 parts. And I've always been a fan of the 3-part methodology because we can use two sets of the data that we basically estimated strata splits to make sure that we have good solid distribution between them. We're talking about regression right now, and that just means we're sampling the distribution equally across that space of the target. And we use train and test to evaluate iterations. Like, hey, I'm going to change my alpha value from 0.001 to 0.1. I want to see what that impact has on the trained data against a validation set. So I test that, and I look at some sort of metric that's associated with that. Regression, we're usually using something like root mean squared error, and that's just a noise reduction of mean squared error, where we're taking actuals in the test versus predictions. And we're just subtracting those out, squaring that difference, and then taking the average of them across the entire data set. It gives us a single metric for that model evaluation. And it's pretty good approximation of how well that fit has done. And the important thing is, I shouldn't say the important thing, but one thing that I do that I don't know how many other people do this, but I always do that evaluation on the train data. I know a lot of people don't do that. They just do it on the test. But I want to see the difference in how well the train does against what it was trained on versus how well the model does against data that it hasn't seen, and just eyeball the difference there. And if I see a huge skew between those, where the like RMSE or whatever metric I'm looking at, MSE, MAE, if I see that it's like really low, we're usually optimizing in the lower direction for any of these metrics. If it's really good on the train set and it's terrible on the test set, then I know I overfit. So either I'm leaking the target somehow, or I had way too many iterations for optimization, or my hyperparameters are just garbage. But if they're both equal or relatively close to one another and they're kind of terrible, then I know that my features suck, that I just don't have enough data to properly mathematically explain this relationship, this correlation. If they're both great, then awesome. And I have this third data set that's another holdout, the validation data set. And that's used for when I'm comparing multiple model families. Like if I'm doing GLM and an OLS-based linear regressor, and then maybe doing decision trees regressor, and I'm comparing all three of those, I don't want to use my test data set that's within the model as an adjudicator of the difference between each of these model families, because it's already been seen and I already have that data. So what I want to do is I want to have a true holdout data set that's just used to evaluate, like compare each of these to one another. And that's what I use that third data set for. And that third value is what would be registered as part of a production candidate release. But if I'm looking at linear regression and I've done this evaluation before I'm looking at the summary data, and I want to see, and like, hey, why do these values not match between train and test on MAE, for instance? What is going on here? I'll just pull the coefficients out from the model. Almost every modeling API that's out there has the ability to extract the coefficients. If it doesn't, and there's not a method that you can call on it for get coefficients, they're still there. So look through the source code on the open source package that you're using, or look through the docs. There's going to be something that like they exist somewhere. Most of these packages that we're talking about are Python. It's usually a dictionary entry in the actual model artifact. So in that object, after it's returned after you've done .train or .fit, that data is written to that object. So it's in the init, basically, of the class. So if you don't know what it's called, run a dir command or a var command. Dir or var will basically dump the class dictionary, or the object dictionary, and just look, and you'll see an array of values that the count of those will be the count of your features. And you can just look at them. They're not going to be labeled usually. It's just going to be an array. It's a sorted order array of the order in which your features were provided. So if you're to look at, say, a pandas data frame of that training data set, everything that was listed as your X variables of that pandas data frame, the order in which those columns appear are the order in which the coefficients appear. And what you're looking for there is massive differences between these different features. You're going to see numbers that are infinitely scaled, really, depending on what family of regression you're using. And if you see something that is so far out from everything else, that means it's got some oversized impact to this particular correlation that was fit during the model fit stage. And for a lot of real world problems that people that I've seen done, and people have done the things we were talking about in previous episodes, like, oh, I'm going to put in like going to select star from my source table after I join stuff, and I'll just create a data frame and hope for the best. There's 100 features in there, and I'm going to fit a model on it. And depending on what settings you have for linear regression, there are regularization functions that happen to dampen the weight of positions in the vector that make no sense for the fitting. And depending on what that biasing agent is in there, you could see on your coefficients like just a bunch of zeros, and there might be 3 or 4 coefficients that are actually meaningful. And when you're looking at model explainability and the pursuit of reducing complexity in implementation, when you're looking at those coefficients, if you see some zeros in there, the model's not using it. It doesn't care. It's meaningless data. So just drop them, or at least do a test of dropping those coefficients, those features, and just saying, all right, the model didn't think this was important, so maybe there's no signal here. And then you go back and plot that. If you hadn't already done that proper EDA and you see a coefficient of 0 or near 0, and the actual scale of the feature value is, assuming you haven't, scaled it yourself. But in linear models, you should be scaling most of these things. But if you hadn't, and you see like, oh, the range on this is 10,000 to 100,000 on this continuous, double or float value, but the coefficient's like 0.000001. Why is it de-weighting that so much? So then plot that against the target. And if it's standard scaled and you've changed the scaling from 0 to 1, and you still see this like really small coefficient on this that's way smaller than anything else, plot that. And if it looks like John Wick just rolled up into the room and blasted some shotgun pattern into a sheetrock of a wall, and there's probably no real data signal there for any correlation to be made. But you can validate that, try to fit a very simple regression on those two variables, and basically get an R-square value from that. And if you see an R-square value that is basically a horizontal line, which means there's no relationship between these data points, then drop it, because it's garbage.
Yeah, so you just threw out like 7 really, really good points. I'm going to try to recap, and for the ones that I missed, let's just revisit really quickly. So first one is thinking about accuracy. The accuracy, let's say we're using RMSE, the difference between training and your holdout accuracy is how much you're overfitting. And that's a really important point. I remember, literally this week, I was working with a buddy, and he was fitting an XGBoost model, and he was intentionally underfitting his training data so that it would generalize better. He just was trying different parameter combinations and actually trying to make the model worse. So we started with like 92% accuracy and brought it down to 83 so that it would do better out of sample. So comparing those two accuracies is really helpful. Then you talked a little bit about the different types of accuracy metrics. RMSE is great. What about comparing accuracy metrics between different models? So you mentioned comparing like RMSE on that holdout for, let's say, an XGBoost versus a linear regression model. Are they comparable?
I mean, you would want to always measure as many applicable metrics as you can, but also know that the method in which those values are getting calculated are fundamentally different, because the model architecture is completely different. For instance, any tree-based model, you don't have a continuous response across the entire space. It's discrete. It looks continuous because, in a regression task, you're like, okay, well, I'm getting a float as a return, so it must be continuous across this entire space. If you ever want to test that out, build a really shallow tree on fairly large data, and then group by your prediction value and see how many distinct values you have. And guess what? It's the number of leaves in your tree, and it's not continuous. Linear models are completely different. They are 100% continuous response curve because it's a functional equation that's generating. So you can have infinite responses from a linear model, and that can be both a good and a bad thing depending on what problem you're trying to solve. And if you need to have that bounded, if the model's really terrible on certain unknown or outlier configurations, you could be predicting near positive or negative infinity, which will make your model look really bad on aggregate, like averaged statistic errors. And end users might be like, wow, these guys suck at data science because this one row is so messed up. So take it with a grain of salt when you're looking at the same metric, because you're constrained in one model family and you might not be constrained in another one.
Yeah, for sure. One of the key points is that if you're using identical data sets, the values should transition pretty well. But for instance, if you're fitting a model on a data set X and doing a completely different problem using data set Y, you cannot compare those accuracy metrics because they're like, if you just think about it, they're using different data, so they don't have transferable meaning.
Mm-hmm.
So that's one important point. Another important point is, how do you think about the fact that accuracy metrics like that simplify accuracy down to one number? Because really, accuracy is every single residual. So what are your thoughts on dumbing it down to a mean or a median or something like that? Do we lose a lot of information?
We lose an absurd amount of information. And I can't even begin to tell you how many times I've been burned by that, where I'm using some, like RMSE has burned me more times than I can even count. Where I retrain a model or even have it automated, like a passive retraining system. I'm like, hey, the RMSE is like a little bit lower this time. And it just so happens that we had like a drift that occurred in the training data, that we had a distribution change where the vast majority of cases, it was easier to draw the correlation and fit to that. So the model became really good, like 80% of the data, and it tanked on 10% of the data. And it was kind of like similar on another 10%. But on that tanking of that 10%, because the 80% improved so much, the 10% degradation wasn't really visible in the aggregate statistic. So the aggregate went down and it made it look really good. And then when we actually dug into, because when I say this has burned me, this hasn't burned me in production. I always like double check before looking at something by, as you said, looking at all the individual results. And that's not manually doing that. That's plotting them and then comparing the plots, like a QQ plot, and checking that line of fit. But when you get burned by that, is you have hope that, hey, things are going to go pretty well because, you know, this feature that I added improved this, or I dropped this feature and everything, you know, I get a lower RMSE. But when you look at the actual raw data and see what your outliers are doing, what's the condition of those outliers? Did it all of a sudden break your actual, not your model, but break your project? The thing you were trying to solve, is it now really bad at the thing you're trying to detect or the thing you're trying to get somebody to take action on? And if that's the case, that's why, if that happens, that's when using just those aggregate statistics can be super dangerous.
Yeah, I agree. It's really important to think about what each metric means. So a mean is a lot more sensitive to outliers than a median, for instance. So just thinking that each of those accuracy configurations isn't accuracy in quotes, it is a overall summary statistic of what accuracy looks like for your residuals. And I see a lot of times with more novice, whatever you want to call them, data scientists, ML people, they think accuracy is this holy grail metric, and they don't stop and think about what it actually represents. So a really, really common issue is that a lot of those accuracy metrics scale negative numbers by squaring them to the positive realm. And so if underfitting or underpredicting is an issue in your space, it's really important to think about that. And that RMSE metric will not think about overestimating or underestimating. It'll treat it all the same. Mm-hmm. So just a word of caution that if you are in a space where you're not just optimizing accuracy and overestimating does matter, those metrics aren't always the best option.
Definitely. That brings up the word that you use, accuracy. That brings up the metric in classification that so many people use. Oh, I'm going to check accuracy on my binary classifier. And they don't look at the skew between the labels. Like, hey, my accuracy is, 99%. This is awesome. And it's like, yeah, well, 99% of your data are zeros. 1% are ones. So your model actually is predicting all zeros. So it's terrible. It's so underfit that you'd be better off blindfolded throwing darts at a dartboard. And if you get a bullseye put a 1 down for that row. Otherwise, put a 0 down. So yeah, those summary statistics they're problematic if you don't follow what Michael just said.
Yeah. And then the third thing that you mentioned was coefficients, right?
Mm-hmm.
Cool. So I'm glad that you brought up that you need to make it scaled so that a 1 unit change in X leads to a certain change in Y. Often, if you have if the scale of your predictor variables are very different from each other, those coefficients lose meaning. Because if you have a scale of 0 to 100,000 versus 0 to 1, a 1 unit change in one metric is very different from a 1 unit change in your 100,000 metric. So standardizing or normalizing to a similar scale is really important. Finally, as you said, you can conduct hypothesis tests on the statistical significance of those coefficients and of those variables to see if they're actually meaningful. So yeah, did I miss anything? I feel like I did.
No, I think that was mostly about what we talked about. Yeah.
Sweet. Cool. So then let's wrap up linear regression with what are some common visualizations you use? Because a picture tells 1,000 words and they're really useful for explaining to stakeholders what's going on. So if they see a line up and to the right with revenue on the y-axis, they're very happy. So what are some tools that you usually use?
I mean, I'm old school. I love me a good scatter plot. Love it. And I think it's the cleanest way to sort of demonstrate what the results are from a regression problem. Y-axis is predicted, x-axis is actual, or swap them. Depends on what your preferences are. Just make sure they're labeled. And what you want to do is draw a line from the origin 0, 0 up through, basically draw a ray from 0, 0 up to 1, 1 and continue it until infinity on your plot, whatever your scaling is. And that is your target. You want a really well fit regression problem will have your predictions and your actuals matched along that 45-degree angle. There are names for this plot. There's visualization packages that you can use to generate these. But that error plot and the estimation that you get from that, the visual representation of R square, what is the relationship between predicted and actual? I always generate those values. I'll print out on the plot MAE, MSE, RMSE. If I did hyperparameter tuning, I'm generating those sorts of plots with MAPE and some of the other metrics that are deterministic for the hyperparameter tuning, which uses a factor in there, which is how many hyperparameters are part of the model, so that it can tell you what the relative effectiveness of your changes were in each of your hypothesis tests. Yeah, I'll use that. If I need to do a summary statistic plot on a regression problem, I'll generate stuff like a PDF or a PMF for classification. And that distribution function that I'm generating, I will generate that and overlay the actuals versus the predicted. And that gives me a kind of a feel for hey, is it predicting the same sort of distribution here on holdout data? How far off am I? And that can help you identify hey, this model is very poorly constrained in this space. Maybe in where I'm intending to predict, if my problem is to predict values in a range of 50 to 5,000, and I'm really good at predicting 50 to 500 range. I have really good conformity there between predicted and actuals. But on my right tail of that, above 1,000, the model just sucks at being able to identify that. Then that can help let me know that I need to go back and do some feature engineering and maybe generate some features, or I need to split out data with some identifier that can help build a correlation a little bit more effectively on with the OLS solver.
Hi, this is Charles Max Wood from Top End Devs, and lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. Whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out. and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
Yeah, I'm on board with all those. I usually keep it pretty simple in that I'm very cognizant of who my audience is. If it's a non-technical stakeholder, I always use MAPE. Percents are a lot more interpretable. And then like a scatter plot showing that it's a good fit. So ideally there's some trend, and that's about it. Maybe some feature importance as well with the coefficients. If I'm presenting to data scientists or my team for feedback, then I usually stick to RMSE. RMSE isn't as interpretable because it's just a big value and it's scaled to the units of your Y variable. So you can interpret it, but it's not quite as intuitive. And for someone who's not technical, it might be a little harder to make intuitive understanding of what's a good RMSE versus a bad one. Then, like you said, the accuracy plots, or like a QQ plot with one prediction or predicted on the Y and observed on the X, super valuable because it shows where your accuracy might be diverging. And yeah, beyond that, that's usually what I use. But the nice thing is that a coefficient is so interpretable. It's actually really difficult to interpret it correctly if you're doing inference, because holding stuff constant is just a mind-boggling concept. But usually it's if X changes by 1, then Y will change by 3. Done. Beautiful. Move on. So that's what I usually use. I'm a big summary statistics guy, and then a fancy plot for my slides.
Yes.
Cool. So that is more or less concludes linear regression. When we move into decision trees now, a lot of those concepts can be applied. So all the accuracy stuff, basically anything that leverages the residuals of our model can be applied. So QQ plot of predicted versus actual definitely can be used. RMSE or other things like that can also be used. But what are some things that are specific to decision trees in terms of model explainability?
The architecture of how trees determine their internal structure is very different from a linear model. So linear model is, as we said, it's an equation with coefficients, and it's basically just algebra. There's no real magic behind when you look at the output of it, of like the model construction. You're like, oh, okay, this is linear algebra. It's pretty straightforward. Trees are different. Trees are logical constructions. So it's a series of if-else statements or case statements of saying, hey, if feature 3 is less than this value or great, then I'm going to go down to my next stage, which might be feature 7 is greater than or equal to these values. And I move down another level and I say, okay, feature 4 now is less than or equal to these. And then another level might be feature 4 again. And we're trying to split out where we have a signal effectively. And that signal is a determination of a random split within that continuous space of values, or that ordinal space of values, where we make a physical split of the data. We calculate what the error would be, and the basically the variance reduction to say, hey, if we split the data here, do I have a reduction in variance in group A versus group B? And that's how the tree is constructed. It iteratively goes through and does that exact operation many times. So at the top level, it's going to go through every feature and it's going to do splits. And it's going to make a determination to say, which one's the best? Like, where do I have the best reduction in variance, the best entropy gain if I split the data here? That's your top level. That's the first split. And then it segregates out that data into 2 parts based on that split condition. And in those 2 parts of data, it does that same operation again. And it continues to do that until it either hits a maximum number of iterations or a maximum depth that you set via hyperparameter, or some other conditions like, can I make a split with this number of leaves in the external node? So all of those things are defaulted. You should be tuning them and you should be tuning them to your particular data and project use case. And you should be running a lot of experiments when you're dealing with tree-based algorithms to understand what are the implications for my prediction if I effectively group out all of my outliers in one bucket of decision and have it so that they're always going to predict this one thing. So it's kind of how trees work. Forests are a version of trees. Most people use forests, like gradient boosted trees, XGBoost, like GBM. Most people use those approaches because they're more robust. They're harder to overfit than a decision tree is, but they all use decision trees under the covers. They're just a forest of trees. So it's taking a bunch of, you take 20 features when you're building that forest. Each of those trees in that forest are going to be taking a sample of either or and a subset of rows, subset of columns, or subset of both. And they'll build their own trees, and then you aggregate where those splits happen and have effectively a voting mechanism. Like, hey, out of 1,000 trees, where did everybody make their first split? And I'm going to vote for whatever was the most popular first split, that's the one we're going with. And you continually aggregate all of those results until you have a final if, else, if, else, if, else, if, else, if, representation. If anybody's ever curious, if you've never done it, I highly recommend it. Actually pull the decision logic from a trained either random forest or probably don't do it on a random forest. If you do a decision tree, regressor, or classifier, pull the decision logic from it. You can visualize it in whatever language you choose. They all support it. And it looks like a case switch statement in SQL. It's like, if this column is above this value, then do this, else do this, else do this. And it's just, you can get this visual representation in text of what this tree actually is. And if you build a visualization, which a lot of APIs have those, they're taking that data and just making a graph out of it.
Yeah, that was actually a really fun project that I did. Decision trees are so pretty on slides. Like a scatter plot is great, but a good decision tree that says, if you do this, revenue equals plus 5%. If you do this, revenue equals minus 5%. That gets people going, because that's fundamentally what a business decision is. You can't increase a business decision by like one value of a coefficient or two. Usually it's do this or don't do this. Usually it's a Boolean action. Sometimes you can increase it. Let's say increase revenue spend in this area, but Boolean decisions are so useful. So I'm glad that you brought up visualizing those decision trees. Then if we think about the splitting of the decision tree, how do we know what features are important? So let's say we are predicting points per game in an NBA game, and we have a player's prior points over all of the last seasons, players' minutes per game, and we have their field goal percentage. So the percentage of shots made over the total shots attempted. How would we think about what of those three features would impact points per game?
I have no idea about that particular sport and all the metrics you just gave.
Well, we can switch it up. Pick a sport.
I mean, if we're just looking at, the reason I said that flippantly was it doesn't matter what the problem is of the data we're looking at. If we're using a tree, we're letting it figure out what that information gain is. So the algorithm that is employed by usually the default in most applications is Gini. And the Gini algorithm is going to go through and iteratively keep track and make decisions on variance reduction and the differential entropy calculation or the variance reduction. So we want to create order out of chaos. And that's what Gini is doing, is it's going through and evaluating these splits and saying, okay, I split on this particular feature at this value this many times, and it created this amount of order out of the chaos that was pre-existing. And you basically just sum those up and you say, for what are those three features that you mentioned, if we look at that particular feature and it was used as a primary split 7 times in the tree, and Those 7 times each had anywhere from 0.12 to 0.34 variance reduction metric associated with it. We're going to add those all up. And if that happens to be the highest one of all of those features, that's what gets the feature importance. It's very useful to look at that from the model, but it's also super dangerous. So I've seen it so many times, even with some senior data scientists, where they generate that feature importance plot from the model. And then they say, well, the reason that we're predicting this is because of this. And they instantly go into sort of causality mode while looking at the feature importance splits of like, well, the reason we're predicting fraud here is because this column's so important, and look at the value here. It's like, that's why the correlation was there, but you can't say that that feature now needs to be manipulated in our business in order to make more of what we want happen. Like that's not how this works. We're just looking at the data that we have for this problem, and the algorithm is just saying, where do I have the most amount of entropy split gain here? And it has nothing to do with causality. So that's the only caveat that I wanted to make sure that we talked about.
Yeah, for sure. Do we have to think about scaling our metrics like we did with linear coefficients?
The algorithm will handle that for you for feature importances out of a tree. So it's going to, when you say, hey, give me the feature importances for certain libraries, you're going to get a raw score, which will be like, hey, these are the Gini numbers. They're usually not that interpretable unless if you've really dug into the code of how these algorithms work and maybe had to implement one yourself, you'll understand what they are. But for most end users, the raw values don't really mean that much. And it's not really worth your time to dig into that unless you really are excited about that. But the public APIs that are in existence for most of these libraries, when you say, hey, give me feature importances from a random forest, it's going to do that aggregation for you. And it's going to give you a sorted ranked ordered list of like, hey, this column was split more often, or this feature was split more often than other ones. And here's a representative value. One of the most famous ones that people generate is the XGBoost one. And that has numbers associated with each of those. And it's a corollary to the Gini calculation that happens. The numbers are important when in reference to other ones, but not, empirically important.
Yeah, agreed.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
I tend to stay away from feature importance more than from a feature selection perspective. Reporting them is usually really pretty, but as you said, people tend to infer causality, which is not almost ever what we can infer. Right. So they're really nice to see, but I've been burned by reporting them and people being like, oh, well, let's just do this. I'm like, you can't make that conclusion. But yeah, what are some of the, let's say if you could use one tool to explain a decision tree, what would it be?
If I could use one tool to explain any model, would be SHAP, or any tool that's based on Shapley's additive explanation algorithm. That foundational paper from, I don't remember when it was written, but it's an awesome paper. If you haven't read it and you're in the data science ML space, you should give it a read. It's like the gateway drug to game theory, which is fascinating because it explains it in reference to our profession and gives you this exposure to thinking through a problem in a very unique way. And the implementation is elegant. Unfortunately, that algorithm can't really be applied to modern ML because of the data sizes that we usually deal with in training data sets. Even if you're thinking about a problem, you're like, oh, I don't have a big data training problem. I only have 250,000 rows. Well, the computational complexity of the original SHAP algorithm is number of features times number of rows times number of rows. So that exponential relationship that exists is mind-boggling for even a modern state-of-the-art computer to process. That's why the approximate SHAP values are calculated in like the Python SHAP package, which is an amazing package that is very widely used by people that are serious about ML in production and about explainability. The core way that it works just delights me. So what we do is we go through each row of the data, and let's say we have 10 features in that vector. In order to determine what the impact of, say, feature 1 is on the model, the only way that we can figure out what that will do or what its impact is if we change it and hold everything else constant. So the original algorithm is to drop it from the feature vector and then run a prediction. So run a prediction with that feature included and then run a prediction without that feature included. You can't do that in like any modern data science API. Like Python, like scikit-learn models don't support that. You can't just drop a feature. It needs to be there. So what the Python SHAP package will do is it'll borrow from the population. So it'll randomly sample your data set and just take a value from somebody else. It'll do that many, many times, and then it'll average the results to give you sort of this safer view than if you just selected potentially an outlier value that could really screw up the SHAP value. But you do that unmolested prediction of like the original feature value, our feature vector through the model, get that prediction, then do the substitution prediction, and you just subtract the two. For regression problems, for classification, you're going to determine like, is this the same? What is the probability of class membership for these two? So if that row was predicted without manipulation as belonging to class number 2, and then with manipulation, it's class 0 or class 1, what was the probability that it was actually of class 2? And we look at that difference, and you actually determine how far off or how close that prediction was. You iterate through each row of the data and each feature multiple times doing this. And at the end, you get this approximate estimation that's more computationally friendly to computers of each feature's impact on each row. You can aggregate that, summarize it on the feature level, or you can expose the explainer, and SHAP does that, where you can say, you can take any arbitrary row of data and run it through there, and it will tell you what the impact is on each feature from manipulating it. So it gives you this amazing overview of a model agnostic approach. Now, SHAP has a lot of APIs associated with it. So it's got its own solvers for different model architectures that are optimized for that space. So you have a linear solver that is highly optimized for linear problems. The way it interacts with the linear model is much more efficient. What I just explained before was the kernel solver, and that's, you can take anything. You can take a TensorFlow model and run it through there. You can take a polynomial equation that you generate in code and you're passing the coefficients in. You can do anything. It's really slow because it's that sort of brute force iteration. But the specific solvers, so there's like a deep learning solver that's optimized for deep learning frameworks like PyTorch and TensorFlow. I don't know if they do MXNet. Sorry, MXNet fans, but they have one for tree-based algorithms, and the way that it's calculating its SHAP values is slightly modified for each of these architectures. And there's some very clever things that the community and Scott Lundberg is the creator of that package in Python. Some very creative things that he and the community have done to get those values for these different architectures in very performant ways. Yeah, so if you haven't used that package or heard about it or checked it out, definitely go read the docs on it. Check out some blog posts that people have written about it, because it will help diagnose a model and what is actually going on each of those features better than any tool that I've used. And then there's another side of stuff, as we're kind of getting short on time here towards the end. The only other thing that I wanted to add with a cool tool that you can use is like What If, which is a simulator. And that simulator will modify features dynamically and it'll say, like, you can basically instruct it to say, hey, I'm trying to predict loan acceptance. Well, I want to simulate keeping everything else standard across my entire data set, all these other features. I want to change income, and I want it to go up and down by this amount of tens of thousands for each row of data, and tell me what the differences are. Like, how does it change? And by analyzing the output of that algorithm, you can start uncovering seriously dangerous stuff with your model, like bias, things that you hadn't even thought of. Like, hey, what if I change geographic region for these customers into a region that has history associated with it of like racial segregation? Does that change? Like, do I have a different basis response on income if I change geographic location for this model that I've trained that I thought didn't have any bias? Usually when you run a model through real world data, it uncovers things that you weren't expecting. Almost every data set is biased because we as humans are biased, and we have flawed decision logic, and we have history and all sorts of nasty things that have been perpetuated throughout the millennia since, civilization started, and they continue to be problems. But so if you want to make the world a better place with your models that impact people's lives, run it through these tools and try to uncover what relationships exist that aren't good for society, aren't good for people. And it can expose those in a way that you can correct your model, correct your features, change your features in order to eliminate that. Maybe add weights to a particular value so that it can be less biased.
Yeah, I've seen Shapley be the state of the art and the default for a lot of people. State of the art, I guess, is the wrong word, but it's super effective and it's a very good out of the box solution. It is pretty computationally complex, so if you can use variance reduction in your decision tree, maybe start there. But it's a great tool. I've used it a lot. I've seen it used a lot. So yeah, thank you
its
for
big
that.
competitor is Lime. Lime got there first, but Lime uses a different fundamental theory in predicting in how it computes its sort of feature impact to a model. And I used Lime many years ago, and I was like, wow, this is such a cool package. But as your data scales, it does not scale well. It's like an order of magnitude more computationally intensive than SHAP is. So if you have a relatively small data set, Lime's great. In fact, SHAP wraps Lime. So if you really want to compare the two algorithms, there is a sort of a developer API in the recent versions of SHAP that you can actually just call a wrapper around Lime, and then you can say, oh, here's the difference between these two. But don't expect them to be executing in the same amount of time.
Yeah, no, never used Lime. Don't plan on it, but maybe one day.
It's clever. That's a clever implementation. All right. We're pretty much up at the time for this week's episode. This was fun. Hopefully everybody got some insight from both Michael and I on things that we think about when we're getting ready to push something to production, or when we're just getting through the iterative cycle of experimentation on solving a problem. These are the sorts of things you do this. And for a major project, you'll do this somewhere between 10 and 100 times of going through and iteratively looking at your SHAP values and being like, nope, that's broken. Okay, we got to go fix this. I got to go get some more data here. I need to drop this data. I need to scale this data. And this is the process that you iteratively are going through to really validate. And the reason behind it all is the reason behind anything that we do as ML engineers or as data scientists. It's all about preventing headaches in the future. We don't want production problems. Nobody wants a PagerDuty alert. Nobody wants to be called before the board of directors or the C staff to explain why our model blew up. So yeah, hopefully it was useful. Next week, I think we're going to be talking to some guests again.
Yep.
So that'll be an exciting discussion. And any closing thoughts, Michael?
Nope. Well, actually, I can think of one. This stuff is super important, and the basic tools take you a really long way. You don't need fancy stuff to explain models. Deep learning, different story. But with these things, Shapley values, looking at coefficients, looking at accuracy, and just thinking critically is incredibly valuable.
Yes. Could not agree more. All right. So until next time, I'm Ben Wilson
and Michael Berg.
And thanks for tuning in, and we'll catch you next time.
Thanks, everyone.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN.
Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.